And crystal field theory will abbreviate CFT. And crystal theory is solely based on an electrostatic model. And essentially what we're saying here in crystal field theory is most of these ligands are Lewis bases. They're electron pair donors. So they have these lone pairs that they're going to donate to the transition metal center. The transition metal center, if I'm the nucleus, I have a bunch of protons in the nucleus. But there's a lot of electrons along the outside of this. So when this lone pair starts to interact with the electrons on the transition metal, we have two electrons coming together. Two electrons coming together in the same place. Is that good or bad? People are shaking their head. No, it's bad, right? There's going to be a repulsion. So when that repulsion happens, the orbitals are going to go up in energy, or they're going to become more unstable. So what crystal field theory does is it only treats the antibonding molecular orbitals, which I'll abbreviate MO, and ignores bonding and non-bonding molecular orbitals. And this is going to make our life so much simpler. So we're just looking at these high energy antibonding orbitals, and we can rationalize through this by saying there's going to be some kind of electron-electron repulsion. Okay? There's also going to be a force of attraction that causes those bonding orbitals to go really far down in energy, but those orbitals don't really come into play when we talk about color or when we talk about magnetism, so we're going to completely ignore those. Okay? So this crystal field theory is great in terms of explaining a lot of the physical properties that we're looking at. So what we can say about this now is that according to crystal field theory, the energies of transition metal d orbitals after they interact with a set of ligands is a function of the relative positions of the ligands and the individual d orbitals. So what this is basically telling us is that when we're analyzing these complexes, and when we're analyzing the excitations that occur in these complexes, there's two things that we really have to consider. The first thing that we have to consider is the shape of the d orbitals. And the second thing that we have to consider is the arrangement of the ligands around the central atom. Because when these bonds form, the orbitals are going to overlap. We're going to consider these ligands more like these spheres or these bunch of lone pairs pointing at the transition metal center. But we need to know the shape of the d orbitals, and we need to know kind of where these ligands are pointing in order to quantify this overlap. And remember, we were talking back earlier in this unit about the electromagnetic spectrum, and it spans this large range. And the visible part of the spectrum is this tiny little sliver in the middle. It just so happens that when a ligand interacts with a d orbital, the splitting or the difference in energy between the resulting d orbitals is right in that little sliver of the visible portion of the electromagnetic spectrum. And this leads to some fascinating properties. So we need to know the orbital shapes, and we need to know where the ligands are positioned and what their geometry is.